Hi, welcome to the 5-minute video of the paper, Removing the Bias of Integral Post Regression. My name is Kerui and I am a PhD student at Department of Computer Science at National University of Singapore. Let me first do a brief introduction of this task. For each crop image containing only one human, a backbone-like simple baseline or HRNet is employed to output heat maps where the value corresponds to the probability of being the correct joint. For detection, there are ground truth heat maps generated from ground truth coordinates, which is a 2D Gaussian around the GT coordinate. For integral post regression, soft argmax is deployed to directly generate the joint coordinate, which takes the expectation of the heat maps. Another difference is that the integral post regression is based on the joint coordinate, which contains no pixel-wise supervision. Nowadays, detection-based methods are dominant in the field of 2D post estimation. Then we beg the question, does detection really outperform regression? Our contributions are threefold. First, we discovered an induced bias of integral post regression and proposed a simple composition scheme. Second, we do a fair comparison of detection and regression-based methods using different backbones and show that regression actually performs better in hard cases. Finally, we propose a joint framework to better utilize the both benefits. We first introduce the induced bias of integral post regression in the 1D space. Assume we have a 1D Gaussian distribution plus some tail with zero value here, as the expected value is the summation of values over all positions, and actually values which equal to zero, and it's the tail here does not take effect. The expected value overlaps with the argmax results because it's metric. However, when the values are normalized by the softmax function, the tail part becomes non-zero, which drags the expectation line to the right side as the tail appears at the right side of the distribution. In this case, expected value no longer equals to the argmax results, and the shift, we call it 1D bias. So when we go to the real application, human post estimation, which is under the 2D or 3D space, the bias still exists. From the figure, we can see that the expected value, the white square, only overlap with the true joint coordinates when it's at the center. However, we know that it can locate it anywhere. It also depends on the scale of beta. Small beta brings large bias, while large beta makes the back propagation of the network difficult. So in this paper, we made a solution for it. We do experiments to choose the best beta, and we propose a simple composition scheme to make the coordinate unbiased. To answer the question, does detection really outperform regression, we do a fair comparison between the detection and the regression. We divide the benchmarks according to the input size, the number of present joints, and the percentage of occlusions. Our experiments show that the regression performs better in hard cases where input size is small, the number of present joints is small, and occlusions are heavy. Based on the two observations and analysis, we propose a joint framework to benefit from both methods. We use the unbiased integral post regression as main loss and use detection loss to provide pixel-wise prior in the initial epochs. The table shows the improvement of our method over detection and regression baselines. More information can be found in the paper, and thank you.